Bismillahirrahmanirrahim. Assalamu alaikum. Hello and welcome to lecture number 26 of differential geometry. Last lecture में हमने mappings of surfaces के बारे में पढ़ा था और ये देखा था कि when a function from one surface to the other surface is differentiable or is a mapping. उसके बाद हमने ये देखा था how we can calculate the tangent map of the mappings. So basically कोई भी mapping अगर दो surfaces के दरमियान given है, then we can calculate the tangent map which will take tangents to one surface to the tangents of another surface. उसके बाद हमने बहुत important class of mappings की थी diffeomorphism, और इन mappings को आज हम ज़्यादा डिटेल से स्टडी कर रहे होंगे क्योंकि they are very important class of mappings in differential geometry. So आज के लेक्चर में हम ये देखेंगे when there is a diffeomorphism between the two surfaces, or in other words when the two surfaces are diffeomorphic. उसके बाद हम ये देखेंगे कि given any mapping between two surfaces, how we can map zero forms, one forms and two forms of one surface to the other surface. So एक surface पे हमने ये देखा था we can define zero forms, we can define one forms and we can also define two forms, लेकिन under this mapping उन zero form, one form, two forms की क्या image होगी ये आज के lecture में हम देखेंगे. So let's recall what are diffeomorphic surfaces. Two surfaces are diffeomorphic if there exists a diffeomorphism between them, or in other words there is a mapping that has an inverse mapping. So there exists inverse of the function which is also a mapping, or in other words the f inverse is also differentiable. और इस केस में हमने देखा था कि in differential geometry this is a kind of equality between the two surfaces. So when the two surfaces are diffeomorphic, we say in differential geometry that they are equal in the sense of differential geometry. And diffeomorphism is a very special kind of mapping. ये surface की चंद properties को सिर्फ देखता है और तमाम properties को नहीं देखता. So you will be surprised कि कैसे दो बहुत different नज़र आने वाली surfaces diffeomorphic होती हैं. And we also did this inverse function theorem जिससे हमारे पास एक simple criteria आ गया था to check when a function is a diffeomorphism. So उसमें basically एक simple criteria था which is a corollary of the inverse function theorem, and the result is if f is a regular and bijective then f is a diffeomorphism. So regular means at each and every point the tangent space is isomorphic to its image under f. So basically Tp of m is isomorphic to Tf of p n. And let's see what are diffeomorphic surfaces. So as I said, this is equality of differential geometry. This is the equality of surfaces in differential geometry. Now diffeomorphic surfaces may differ in shape and size. So अगर कोई सी दो surfaces given है और वो दोनों diffeomorphic हैं तो ये possible है कि एक का size इंतहाई छोटा हो और दूसरे का size इंतहाई बड़ा हो और maybe infinite size हो, और उनकी जो shapes हैं वो बहुत ज़्यादा different भी हो सकती हैं. So diffeomorphism is a very special kind of map जो कि size और shape इन दोनों में differ नहीं करती. Now let's consider examples to see how this shape and size thing can differ. So for example, an open rectangle in R2 is diffeomorphic to the entire plane. So it's diffeomorphic to the entire plane R2. So अगर मैं XY plane में एक छोटा सा open rectangle लूँ which varies from -π/2 to pi by 2, and along y-axis this varies from minus pi by 2 to pi by 2, then this very small portion of R2 is diffeomorphic to the entire plane. So a very small portion of R2, let's say the set D, is diffeomorphic to the entire plane. So in other words, there exists a mapping which is differentiable from this set D to the entire plane R2, and there exists F inverse from R2 to D, and both are differentiable. And now you can observe that the size of D is very small. It's a very small disk in R2, but this is diffeomorphic to the whole plane R2. So this is very strange fact about diffeomorphism. इसमें जो बहुत छोटा नजर आने वाला पोर्शन है R2 का, this is in fact diffeomorphic to the whole plane. So let's see इसको कैसे प्रूव करेंगे हम. Consider this open set R, which is given as minus pi by 2 to pi by 2. So basically this is the same set defined as minus pi by 2 to pi by 2, और हम एक्सिस के नाम दे रहे हैं u and v, और along v axis this is also minus pi by 2 to pi by 2. Then the function f from R to R2 is defined as, then the function f from R to R2 defined as f of uv is equal to tan u tan v is a mapping of R into R2. Now why this is differentiable? Because tan u is differentiable, tan v is differentiable. So the differentiable part is okay. Now why the image of this map is each and every point of the plane? क्योंकि आप tan x के ग्राफ को गौर से देखें. Let's say this is y is equal to tan x. Then between minus pi by 2 and pi by 2, the range of tan x is the whole of the y-axis. So in other words, अगर y-axis का मैं कोई सा भी point ले लूँ, then it is basically image of some value of x under tan x. So corresponding to every point on the y-axis, there exists a point on x-axis such that the image of this point on x-axis is this point along y-axis, and this is true for each and every point on the y-axis. So इसका मतलब है कि y-axis का हर point tan x का image point है. So इसका मतलब है the range of tan x is basically all of y-axis. So जब हम minus pi by 2 to pi by 2 travel करेंगे, then we will be covering all of the real line. So इस केस में आप देख सकते हैं u varies from minus pi by 2 to pi by 2 and v varies from minus pi by 2 to pi by 2. So इसका मतलब है tan u जो है ये भी वेरी कर रहा है to whole of the real line, और tan v भी वेरी करेगा to whole of the real line. So this will take each and every real number, and this will also take each and every real number. So this f of uv is basically an onto map. Onto map means each and every point of R2 will be an image of some element of this set R. क्योंकि this is true for tan u, this is true for tan v, so this is true for this ordered pair. So we have defined a function from this very small set R into the whole plane R2, और ये जो मैप है ये onto मैप है. So each and every point of R2 is image of some point of this set R in R2. Now we have seen that f is differentiable. Let's calculate f inverse. So in this case calculation of f inverse is simple. So f inverse of uv is equal to tan inverse u and tan inverse v, and we also know that tan inverse u and tan inverse v are differentiable. So it means f inverse is also a mapping. So f is a diffeomorphism because it has an inverse which is also differentiable. So similarly every open rectangle in R2 is diffeomorphic to R2. So R2 के अंदर कोई सी भी open rectangle ले लें, it will be diffeomorphic to the whole plane R2. So diffeomorphism does not respect the size of the objects. बहुत छोटा नजर आने वाला ऑब्जेक्ट डिफ्यूमॉर्फिक हो सकता है to a very very big object. Now let's consider another example. The sphere minus 1 point to R2. आप एक sphere ले लें, उसमें north pole आप निकाल दें. So then we can see that this sphere is the same as the whole plane R2. So once again last example में हमने देखा था कि diffeomorphism does not respect the size, which means बहुत छोटा नजर आने वाला ऑब्जेक्ट बहुत बड़े ऑब्जेक्ट के डिफ्यूमॉर्फिक है. और इस केस में हम देख सकते हैं कि the shape is not counted in diffeomorphism as well. So for example ये sphere है, it's a very round shape, लेकिन this is diffeomorphic to the whole plane, लेकिन इस sphere में से हमने एक पॉइंट निकाल लिया है. So आइए देखते हैं कि हम इनको कैसे डिफ्यूमॉर्फिक प्रूव कर सकते हैं. So उसके लिए हमें एक मैपिंग डिफाइन करनी पड़ेगी. So let's first consider a patch of the sphere. Now let sigma naught be sphere minus 1 point, and we are subtracting this north pole from the sphere. Then a parameterization of sigma naught is given by x of uv is equal to cosine v cosine u cosine v sine u 1 plus sine v. So basically it's a sphere which is resting on xy plane, or in other words it is touching the xy plane only at one point, and the north pole is 0 0 2, and this is z axis, and we are taking u and v to be vary from r, the real line, cross minus 3 pi by 2 to pi by 2, and we can see that this will cover each and every point of the sphere apart from the north pole. So basically this is covering each and every point of the sphere apart from the north pole. So this is a parameterization, and this is not a one-to-one map. So this is not a patch, it is a parameterization. Now let's define this map, which is stereographic projection of the sphere onto the plane. ये हमने last lecture में भी देखा था, और ये हमने calculate किया था that the image of any point P, which is let's say P is equal to, with coordinates P1, P2, P3, the image of this point under this function f is basically 2p1 over 2 minus p3, 2p2 over 2 minus p3, and 0, and this is basically contained in R2. So each point of the surface is mapped onto some point of the plane R2. Now what is f of x of u? We can put the values of x of uv. Now what is x of uv? This is equal to cosine v cosine u cosine v sine u and sine v. और ये जो वैल्यूज़ हैं जब आप इधर पुट करेंगे, सो दिस इज P1, दिस इज P2, दिस इज P3, इन वैल्यूज को यहाँ रिप्लेस करेंगे तो हमारे पास ये एक्सप्रेशन आ जाएगा विच इज y। और यहाँ से हम इजीली देख सकते हैं that this is a regular map. So how we can see that this is a regular map? उसके लिए हमने लास्ट लेक्चर में डिस्कस किया था कि हम सिर्फ और सिर्फ जो पार्शियल वेलोसिटीज़ हैं xu और xv उनके इमेजेस लेंगे, so xu और xv अंडर द टेंजेंट मैप, और इनको हम yu और yv के नाम देंगे। और how we can calculate these? So we can in fact calculate them by differentiating this y with respect to u and this y with respect to v. So from here we calculate yu and yv, और इन दोनों को हम देखेंगे that these are linearly independent. So if these are linearly independent, then the tangent space 2 R2 in fact, so this is R2 at point f of p is basically two-dimensional, or then this will imply that f is regular. और क्योंकि इस केस में u and v could be any point of the sphere, since this is true for each and every point u and v, so basically this is true that the tangent map is isomorphism, or in other words f is regular. And if f is regular at each and every point and it is onto, then we can say that this is a diffeomorphism. So I am leaving this as an exercise जिसमें आपने yu और yv कैलकुलेट करना है, और क्योंकि इसमें y गिवन है, जस्ट आपने इसको डिफरेंशिएट करना है पार्शियली विद रिस्पेक्ट टू u और डिफरेंशिएट करना है पार्शियली विद रिस्पेक्ट टू v, और फिर आप ये देखेंगे कि हाउ दे आर लीनियरली इंडिपेंडेंट. So this is an exercise to check that why these are linearly independent. और जब ये linearly independent हो जाएंगे, इसका ये मतलब है the image of the tangent space at any point, so the image of xu and the image of xv at any point is basically yu and yv, and they are linearly independent. And if they are linearly independent, then this means that the tangent map is isomorphism at that point. And if the tangent map is isomorphism, which means f is regular at that point, and since u and v could be any point of the sphere, it means f is regular at each and every point, and then this implies that f is a diffeomorphism. और इस केस में भी आप देख सकते हैं एक sphere which is a very round shape, it has a curvature, but it is diffeomorphic to the whole plane, which is very flat. So this is the different observation about the diffeomorphisms. लेकिन एक चीज़ जो आप नोट कर सकते हैं कि हमने स्फीयर में से नॉर्थ पोल को निकाला हुआ है. So sphere minus 1 point is diffeomorphic to the plane. Now let's consider another example, a cylinder and R2 minus a point. Now what is a cylinder? A cylinder in R3 is defined as an object which is basically a circle at each and every plane parallel to xy plane. So this is the red circle in xy plane, और उसके अलावा कोई भी आप plane लेंगे parallel to z axis, then it will again be a circle in that plane. So that's how we define a cylinder. और जो cylinder है, it is basically diffeomorphic to R2 minus a point. So R2 minus 1 point is diffeomorphic to the cylinder. Now let's see how we can prove this. We define a map from this cylinder. So why this is a cylinder? Because there is no z variable involved in the equation of C, so this means that this is all the way circle for each and every value of z, and it is a circle with radius 1 and center origin at each and every plane. So if we combine them all, it will become a cylinder. And we define a map from cylinder to R2 in the following way: e raised to power z x y. So basically आप सिलेंडर का एक पॉइंट लेते हैं और उस पॉइंट को आप मैप कर रहे हैं टू अ पॉइंट ऑफ द प्लेन, एंड दिस e raised to power z is basically the magnification coefficient. So basically जैसे जैसे आप z की वैल्यू बढ़ा रहे हैं, e raised to power z एक्सपोनेंशियली बढ़ रहा है और ये आपको पॉइंट्स दे रहा है which are basically on a straight line. So f maps bijectively C to R2 minus this origin. So basically this map is basically mapping each and every point of the cylinder to all of the R2 except for one point. Now the inverse of f can be calculated, and this is not part of our course to calculate how this f inverse comes, but by observation f inverse is given as u over u square plus v square square root, v over u square plus v square square root, and log of square root of u square plus v square. So this is the inverse, and we can also see that this function f is differentiable, and this f inverse is also differentiable, and the map f defined in this way is also bijective. And so if this holds, then f is a diffeomorphism. So basically a cylinder is diffeomorphic to the plane minus a point, or in differential geometry they are equal. Now let's start with the next topic, which is mappings of differential forms. So मेरे पास differential forms given है एक surface पे और एक mapping given है between the two surfaces. How can I map differential forms from one surface to the other surface? So for example, this is the surface M, and this is another surface N, and there is a one form, let's say xi, on this M. Then what will happen to f of xi? Is it possible that f of xi is differential form on N? So this is the question mark. What is f of xi under this map? So let's first consider the zero forms, which are just functions from M to real line, and which are functions from N to the real line. So let's start from the zero forms. Let g from M to R is a function, and it's a zero form on M. So basically there is a function f taking each and every value of M to the real line. Then what will happen to f of f? Is it possible that we can translate this function f, which is zero form on M, to some zero form on N? And the answer to the question is no, this is not possible in general, but one thing can be done, which is if I take a function which is zero form on N, so it is a function which can take values of N to the real line, then I can pull back. So I'm using the word pull back क्योंकि जो f की डायरेक्शन है वो from M to N है, लेकिन मैं जो जीरो फॉर्म्स हैं n के ऊपर उनको पुल बैक कर रहा हूँ टू जीरो फॉर्म्स ऑन m, और इसको मैं कैसे डिफाइन करूँगा? सो बेसिकली f of f, and here f is basically, so let's say this is f prime, so here f is basically a zero form on n, so it takes points of n to the real line, and we can define f of f to be a zero form on m. So let's say p be a point on m, then f of p is equal to, सबसे पहले आप इस पे f अप्लाई करेंगे और उसके बाद आप स्मॉल f अप्लाई करेंगे. सो इफ p is a point in m, then f of p is a point in n, और अगर f of p n का पॉइंट है, then I can apply this small f on this f of p and I will get a real number. So basically it is a real number. And what is the input? Input is points of m, so we are taking points of m and we are giving as an output real numbers. So a function which takes points of the surface and gives real numbers as the output is called a zero form. So basically f of f is a zero form, और इसको हम कहते हैं this is the pull back of f. इसको मैं once again बता दूं pull back क्यों कह रहे हैं, because the direction of f is from m to n, but we are pulling back the zero forms on m to the zero forms on m, or sometimes हम इसको लिखते हैं the pull back f upper star f. So ये notation हम in general use करते हैं for the pull back of this zero form. Now let's consider what will happen with the one forms. Now let f from m to n be a mapping of surfaces, and let phi be a one form on n. Now the pullback of phi written as f upper star of phi is defined as, so once again इस केस में भी हमारे पास सेम प्रॉब्लम है कि मैं कोई सी भी जो वन फॉर्म गिवन है किसी भी सरफेस m पे उसको पुश नहीं कर सकता इन द डायरेक्शन ऑफ f, कि अगर किसी सरफेस m पे वन फॉर्म है और देयर इज अ मैप फ्रॉम m टू n, देन आई कांट टेक इमेज ऑफ दैट वन फॉर्म टू सम वन फॉर्म ऑन n. लेकिन इस केस में भी मैं ऑपोजिट डायरेक्शन में जा सकता हूँ, पुल बैक कर सकता हूँ. सो बेसिकली अगर मेरे पास फाई कोई वन फॉर्म है n के ऊपर, then I can pull back this phi and I write it down as f upper star phi. और इसको हम कैसे define करते हैं? Now what is a one form? Let's just recall one form. A one form is a function. One form is a function that takes tangent vectors to real numbers, and it is also a linear function. So this is a very rough definition, लेकिन in general what is a one form? It takes tangent vectors as input and gives real numbers as output. So what is the domain of a one form? These are tangent vectors. So हम देखेंगे कि how to define f upper star of phi on m, क्योंकि अगर हमने ये देखना है कि how we can pull back a one form on n to some one form on m, तो हम इसका image define करेंगे for some arbitrary tangent vector v to m. और ये हम कैसे define करते हैं? This is defined as phi of f lower star of v. Now if we see what is f lower star of v, now this is the image of this vector v under the tangent map. So tangent map क्या कर रहा है? Tangent map of this mapping f takes tangent vectors of m to the tangent vectors of n. So basically it is a tangent vector to n. So f lower star of v is a tangent vector to n. So अगर ये tangent vector है n पे and phi is a one form on n, then we can surely apply phi on this tangent vector to n. So हमने define कर दिया है, given any one form on n, we can pull back it to some one form on m, and it is defined as f upper star phi of v is equal to phi of f lower star of v. So इसमें जो भी वेक्टर होगा जो कि m पे है, इसको आप इसका इमेज ले लेंगे अंडर दिस टेंजेंट मैप और उस पे जस्ट phi अप्लाई कर देंगे. So that's how we define the pullback of a one form from n to m. Similarly, we can define a pullback of a two form. So how to define pullback of a two form? Given any two form on n, the pullback of eta, which is the two form denoted by f upper star eta, is defined in the following way. Now once again, if I have an eta which is a two form on n, then I want to get a two form on m. So what is a two form? So a two form is a function which is from the pairs of tangent vectors to real numbers and it is linear in both coordinates. So ये हमने definition की थी two form की. अब इस केस में अगर मैंने ये देखना है कि how this two form is defined, तो इसका मैं image define करूँगा on a pair of tangent vectors. So let u and v be a pair of tangent vectors to m. So u के लिए for example ये curve है हमारे पास और v के लिए curve alpha है. Then f upper star eta of uv is basically defined as f lower star of u, f lower star of v and eta. Now once again हमने क्या किया है, जो tangent vectors थे u and v to m, उनका image ले लिया है under the tangent map. So this is the tangent map. Under this tangent map we get f lower star of v, and under this tangent map we get f lower star of u. So we get two tangent vectors to the surface n. So we have a pair of tangent vectors to the surface n, and hence we can apply eta, which is the two form on n, on this pair of tangent vectors, and we will get a real number. So that's how we define pullback of a two form to the surface m. Now the essential operation on forms are sum, wedge product and exterior derivatives, and they are all preserved by the mappings. Now for example, consider this theorem. F is a function from the surface m to the surface n, and it is a mapping, which means it is a differentiable function, and xi and eta are two forms on n. Then the pullback of xi plus eta is equal to the sum of the pullback of xi and pullback of eta. And similarly, the pullback of the wedge product of xi and eta is equal to the wedge product of the pullbacks of xi and eta. And similarly, the pullback of the exterior derivative of this differential form is equal to the exterior derivative of the pullback of the differential form. Now these properties will be used in our next lectures, or they are also useful to do exercise questions जो कि assignment और quizzes में होंगे आपके. Now let's try to prove them one by one. अब इस केस में they are differential forms. So either xi and eta are zero forms, or they are one forms, or they are two forms. So there are three cases. So case 1. So case 1 में हम लेते हैं, let's say xi is some function which is a zero form, and eta is some function g which is again a zero form. Now what is pullback of f plus g? हमने कैसे define किया था? For some point p of m, this is defined as f of p f plus g. So basically आपने f of p calculate किया, which will be a point on n, and then you can apply f plus g on it, and it can be written as f of capital F of p plus g of capital F of p. Now what is this expression? So this is basically f upper star of f at point p, and this expression is basically f upper star of g at point p. So if this is true for each and every point, then this is true in general. So this is how we prove if both xi and eta are zero forms. Now let's consider case 2. So in case 2 we take both f and g to be one forms. So xi and eta are one forms. So if these are one forms and these are pullbacks, so basically we can calculate their image on some vector v on m. So let v be a vector on m, then f upper star xi and eta at vector v is equal to, by definition this is equal to xi plus eta of f lower star of v. Now f lower star of v is basically the image of this vector v under the tangent map, and it is a vector on the surface n. So we can apply these one forms, which are one forms on n, and we can see that they are equal to xi of f lower star of v plus eta of f lower star of v. So which is equal to, so this expression is the same as f upper star of xi of e plus f upper star of eta of e. So this statement is true when xi and eta are both one forms. Now let's consider the last case, case 3, when xi and eta are two forms and these are two forms on n, and definitely the pullback of xi plus eta is going to be a two form on the surface m. Now if we want to check the equality of these two expressions, then we must check that they are equal for each and every pair of vectors, because xi and eta are two forms. So for that we take v and w, which are two tangent vectors to the surface m, and we see their image under this two form. So if xi and eta are two forms, then the pullback of xi plus eta is also going to be a two form. So let's check its image on a pair of tangent vectors to m. So this is equal to xi plus eta f lower star of v, which is the image of this vector v under the tangent map, and f lower star of w, which is the image of w under the tangent map. So this is basically equal to xi f lower star of v f lower star of w plus eta f lower star of v f lower star of w. So which is the same as saying that pullback of xi at vw plus pullback of eta at vw. So this implies that this is true for each and every pair of tangent vectors to M, and so this is true in general. Now let's consider the second part. So in this part we have to prove that the pullback of the wedge product is equal to the wedge product of the pullback. Now let's consider the case when xi is a function. Then there could be three cases. So basically xi is a function and eta is also a function, let's say g. Then this is very simple, so this is just f upper star fg. So it is very easy to prove that this is equal to f upper star f into f upper star g. So this is simple. So basically what is the domain? So just take any point P of the surface M and prove that this holds for this expression. Now let's consider case 2. So case 2 is when xi is a function and eta is a one form. Now once again this becomes f upper star f eta, and so the right hand side becomes f upper star f into f upper star eta, because this is a function and this is a one form, and the wedge is always used between two differential forms. So this is not a differential form, but it is just a zero form, a special kind of differential form, so we cannot use wedge between them. And how to check they are equal? So we take any tangent vector, because this is a one form and this is also a one form, so we check if they are equal for each and every tangent vector to M. So let's check capital F upper star f eta f v of p. So this is equal to f of p and eta of f lower star of the vector part. Now what is this expression? This expression is just the pullback of f at point P, and this expression is just the pullback of eta at vector. So basically we have proved that the pullback of f into eta is equal to the multiplication of pullback of f and pullback of eta. So this is also true for this case when xi is f, a function, and eta is a one form. Similarly we can prove that what will happen in the case 3 when xi is a function and eta is a two form. Then we have to prove the same thing for a pair of vectors. So take pair of vectors. So let v and w be a pair of vectors. Then calculate f upper star xi wedge eta. So basically once again this is equal to f upper star f eta. So we have to prove that this is equal to f upper star f multiplied by f upper star eta. So this is to prove. So prove करने के लिए हम क्या करेंगे, पेयर ऑफ वेक्टर्स लिया हमने और उसके बाद इसका इमेज देखेंगे. व्हाट इज f upper star of f eta at this pair of vectors v and w. So this is equal to, by definition, f eta f lower star of v f lower star of w. So ये हमने अभी definition की थी. And if p is the point where we are taking this tangent vectors, then this becomes f of p and eta of f lower star of vp f lower star of wp, which is the same as f upper star of f and f upper star of eta. So we have proved this for these three cases. So what is left? So cases left are when xi is a one form and eta is also a one form. इसके अलावा और कोई केसेस नहीं बन सकते, क्योंकि फॉर एग्जांपल व्हेन xi is a one form and eta is a two form, then so this implies xi wedge eta is three form and each and every three form on surface is 0. So this is not the case. इसलिए सिर्फ और सिर्फ एक केस रह गया है in which xi is a one form and eta is also a one form. Now let's see the next case. This is case number 4, and where xi is a one form and eta is also a one form. Now let's see how to prove this. F upper star of xi wedge eta. Now xi wedge eta is a two form, so this is a two form, and if we want to prove this equality we have to take a pair of vectors. So we take this pair of vectors v and w, and this becomes a two form. और हमने ये देखा था how to define the pullback of a two form. So this is defined as xi wedge eta of f lower star of v f lower star of w. Now we have seen that how to define this two form. Now this is equal to xi of f lower star v eta of f lower star w minus xi of f lower star of w eta of f lower star of v. Now this is the same as the pullback of xi at point v, and this is the same as pullback of eta at point w, and this is the same as the pullback of xi at point w and the pullback of eta at point v. Now using the same definition जिसको हम यूज़ करके इस लाइन से इस लाइन पे आए थे, using the same definition we can go back and we see that this is just the wedge product of f upper star xi and f upper star eta at point v w, and this v and w both are tangent vectors. So we have proved this for each and every pair of tangent vectors, so this is true in general. So we have proved this thing for all the 4 cases, and so this is true in general. And once again, let me tell you that this equality will be very helpful in solving the questions of exercise. Now let's come to the last property, where we have to prove that the pullback of the exterior derivative of a differential form is equal to the exterior derivative of the pullback of the differential form. So in this case we will be proving it when xi is a one form, और जो बाकी cases हैं वो simple हैं. So we will consider the case when xi is a one form. So let's see how to prove it. So let x from D to M be a patch in M, and y is equal to f of x. So basically let M is a surface and let N be another surface, and f is a map between them, and we have a patch from some open set to this surface M, and let's say this is the patch x of D, and let y is equal to f of x. So basically this is the y, and it will take points of x of D to some points of N. Now we have seen that to see the image of the tangent map, we just need to see these 2 images. So at any point, let's say if this is xu and this is xv, then basically we just need to see the images of xu and xv, and if there are yu and yv, then we know what is the image of the tangent map at that point. Now we calculate this following. Now if we can prove this for this pair of tangent vectors, then this is true in general. Now by definition, which we just saw, f upper star xi, which is basically if one form in this case is equal to partial by partial u f upper star xi xv minus partial by partial v f upper star xi xu. So this is the definition that we just saw on the last slide. ये हमने पिछले lectures में की थी. So this is equal to by definition of the pullback, this is equal to xi f lower star of xv. So basically it is the same as f upper star xi at xv is equal to xi applied on f lower star xv. So इस चीज़ को यहाँ रिप्लेस कर दिया हमने, और सिमिलरली इस चीज़ को हमने यहाँ रिप्लेस कर दिया, और this is equal to, so what is f of xv, and now what is f lower star of xv? This is just equal to yv, and so this becomes xi of yv. And similarly, what is f lower star of xu? This is yu, which is written over here. Now what is this expression? This expression is just the exterior derivative of xi, which is at point yu yv, and once again this is equal to f lower star of xu f lower star of xv, and so this is equal to the pullback of dxi at xu xv. So हमने इस pair of tangent vector से start लिया था, and we ended up at proving that the exterior derivative of f upper star xi is equal to f upper star dxi. So if this is true for xu and xv, then this is true for each and every pair of tangent vectors in this tangent plane, and this is true for each and every point. So why this is true? Because we can use this property axu plus bxv cxu plus dxv is equal to a dbc and eta xu xv. So this expression does not count, and this is just a real number, and so if this is true for xu and xv, then this is true for each and every pair of tangent vectors, and this is true for each and every point on the surface M. So what we have seen in this lecture, so we have seen what are diffeomorphic surfaces, और इस चीज़ में हमने देखा कि apparently जो बहुत different size की दो surfaces हैं, they could be diffeomorphic. So basically diffeomorphism does not see the size of the objects. और similarly हमने ये भी देखा कि apparently जो बहुत different shape था, for example एक sphere और एक plane, so sphere has curvature and plane does not have curvature, लेकिन अगर sphere में से एक north pole अगर आप निकाल लें, then they are diffeomorphic, or in other words in differential geometry they are same objects. And then we saw how a cylinder is diffeomorphic to a plane minus the point which is origin. So once again इसमें cylinder is very curvy object, but the plane is a very flat object. So but they are diffeomorphic. And then we saw that if there is a mapping between two surfaces, how can we translate or how can we take differential forms from one surface to the differential forms on the other surface. And then we have seen some properties of these pullbacks of differential forms, और ये जो properties हैं ये आप use करेंगे in solving questions. Next time we will be interested in integration of forms. This is the end of the lecture. Thank you very much, and Allah Hafiz.